Now I want to take a look at applications that involve finding dot products of vectors. Vector properties make finding work a really fairly simple process. The dot product of the force vector and the displacement vector gives a scalar result that is the work done by the force. If I let a constant force F be applied to an object, producing a displacement d, if the angle between F and d is theta, then the work done by the force is given by the work is equal to the magnitude of F times the magnitude of d times the cosine of theta. But this is just the dot product of the force F and the displacement vector d. The hardest part of the process is making sure that the units are consistent and that you're keeping track of the direction of your vectors. So let's work an example. I'm given a force F is equal to components 2, 3, 2 in newtons, and it moves an object from point P given by 1, 3, 2 to point Q given by components 4, 4, 1, and these are in meters. What work is done by the force and interpret the result? So the first thing I need to do is figure out my displacement vector d. d is equal to the vector between P and Q, and that has components 4 minus 1, 4 minus 3, and 1 minus 2, so that my displacement vector is given by components 3, 1, negative 1. The work done is the dot product of the force vector and the displacement vector. This gives me 2 times 3 plus 3 times 1 plus 2 times negative 1, or 7 joules of work. If I interpret the result, I'm going to use the relationship that says cosine theta is equal to the dot product of F and d divided by the magnitude of F times the magnitude of d. My dot product of F and d is 7. The magnitude of F is the square root of 17. The magnitude of d is the square root of 11, so that my cosine of theta is approximately 0.5119. The angle between the force and the displacement, theta, is approximately 1.033 radians, which is approximately 59 degrees. Since the magnitude of the force is Since the magnitude of the force is the square root of 17, this is approximately 4.1 newtons. The magnitude of the component of the force in the direction of displacement is the magnitude of the F sub W vector. That is going to be my magnitude of my force times the cosine of theta, square root of 17 times the cosine of 1.033, which is approximately 2.11 newtons. Now let's see what happens when I have parallel and normal vectors. Projections are often very useful when I'm working with vectors applied to objects where the vectors are not cleanly aligned along horizontal or vertical axes. Some common examples include an object on an inclined plane or an object suspended from a horizontal beam by 2 cables, those kinds of situations. Basically, any problem that involves resolving vectors into components that align to an orthogonal set of axes will use projections. There are some key points to keep in mind. A parallel force is a projection of the force in the direction parallel to the plane of interest. The parallel force will determine the tendency of the object to slide down a surface or a plane. A normal force is the projection of the force that is perpendicular to the surface or plane of interest. The normal force determines the tendency of an object to remain sitting on a plane. So I can sketch a wedge that is elevated at an angle theta from the horizontal with an object sitting on the inclined surface of the wedge. A vector that points straight down vertically is the gravitational force or the weight of the object as it sits on the plane. A vector that lies along the surface of the incline is the parallel component of the F force, and the vector that lies perpendicular to the plane is the normal force. Note that we can work with a two-dimensional coordinate system here to keep things simple by twisting my coordinate system so that the positive x-axis aligns with the parallel component of my force along the surface of my inclined plane. Using this shifted coordinate system is usually the easiest way to treat problems involving static equilibrium. However, it is possible that we might have other forces working in our system, and our normal force may in fact point out of the surface rather than into the surface. So keep track of all the forces that are involved in your situation and pay attention to where the normal force might end up being. Let's work an example. I want to find the components of the vertical force F given by the components 0 and -10 in the directions parallel and normal to a plane that makes an angle of pi/6 with a positive x-axis. Show that the total force is the sum of the two component forces. A parallel component will need to be a scalar multiple of a vector that lies in the plane of interest. So we need to identify a vector in the plane that we can use for our projection. The plane of interest lies at an angle of pi/6 with respect to the positive x-axis. Our force acts on the object in a negative y direction, so we will use the vector in the plane given by the vector u is equal to the square root of 3/2 and -1/2. The projection of the force F on the vector u is given by F dot u over U dot u times the vector u. That's equal to 5/1 times the vector components square root of 3/2 and -1/2, which gives me the vector in component form 5 square root of 3/2 and -5/2. A normal component will be given by taking my vector F and subtracting the projection of F onto u from that. This gives me the vector 0 and -10 minus the vectors 5 square root of 3/2 -5/2. This gives me a vector in component form of -5 square root of 3/2 and -15/2. If I draw the sketch of the inclined plane with a component parallel to the surface and a component perpendicular to the surface, it is visually possible to see that the weight vector is the resultant of the sum of the two vector components of F. Now you get to try it. Pause the video and find the components of the vertical force F given by the component 0, 6 in the directions parallel and perpendicular to a plane that makes an angle of 2 pi/3 with the positive x-axis. When you're ready, restart the video to check your understanding. So I want to find the components of the vertical force specified by component 0, 6 that are in the directions parallel and perpendicular to a plane that makes an angle of 2 pi/3 with the positive x-axis. Because the plane of interest lies at an angle of 2 pi/3 with respect to the positive x-axis, this tells me my force is acting in a negative x direction. So the vector parallel to the plane will be given by the vector u is equal to the components -1/2 and square root of 3/2. A parallel component is going to be the projection of my force onto the u vector. That'll be F dot u over U dot u times u. F dot u over U dot u is the square root of 3/1, and I multiply that by the components -1/2 times square root of 3/2. My parallel component will be given by the components -square root of 3/2 and -3/2. The perpendicular component will be found by taking my force vector F and subtracting the projection of F onto u from that. So I'm taking the vector 0, 6 and subtracting the vector -square root of 3/2, -3/2. My perpendicular component is given by the component square root of 3/2 and 15/2. This has been a very quick look at some great application problems that involve using the dot product to determine how to construct projections of a vector parallel or perpendicular to a reference or plane. Be sure and let me know if you have any questions about working with applications that will involve dot products.